Okay, ready? Ready?
Ready.
I'm so tired. Ugh.
Was you had before, Matt?
Excrement.
It's tense.
Oh.
That's the exam for last year. Intake one.
This is hard.
I think today's is hard.
Yeah.
I just can't remember all of them. Like definition, man. I don't like definition. That's most question is definition today. It's around maybe 7 or 8. It's all definition. It's not too much mark. Well,
Some of these I know. Define relative atomic mass. Still, I don't like it.
I don't like it.
Okay, did you write this down? Kinetic model of gas. Somewhere.
Yeah, I saw the
Oh,
Group tutoring.
I don't care about that. Did you write this down?
Okay.
Oh, you moved?
Me?
You moved yesterday? No, when
No,
you moved?
this
Saturday.
Saturday.
Oh, sorry. Okay.
记得吗？
你跟我说的。
What?
Nothing. She's clearer than me. 柠檬精。
柠檬，我操。
Okay. Let's continue. Now, so there's a bit to do. You don't need to write this down because you might remember it. Do you remember what pressure means? What's the form? Pressure is when you push on something.
Yeah.
Do you remember the formula?
F over A.
No.
It's
F over A.
yeah, it's area. I remember the video.
Yeah. And do you remember what the units are?
Square.
Ben? Do you remember the units for
Pa.
pressure?
Oh,
Pa.
Pascal.
Pascal.
Yeah.
Yeah? Remember? And the units are pascals. You remember this, right?
Yeah.
Yeah? Oh, okay. I'm just making sure. And remember we said 1 Pascal, how much is that? 1 Pascal is the same as,
Newton.
yeah?
Meter square.
Newton
Over.
Newton per meter squared. Yeah, okay. I hope it's okay. Right. Now, this is what we're looking at today. Have you heard of this term, ideal gas, in chemistry? No? You've not heard of this? Ideal gas?
Well, what means is either.
Yeah, okay. It's a word from chemistry. It's a gas that's kind of simple behavior. It's not a special gas, just like a simple gas. Are you checking the dictionary? Yeah.
Oh.
You know this in Chinese? Yeah. Yeah. You
So
know?
it's not. It's impossible to achieve.
In real life, some things are like this. So, for the gas to be ideal gas, we need a couple of things. Number one, it has a low density. So if the gas has a low density, it could be ideal. Okay, that's number one, low density. Number two, we imagine the gas as colliding particles. So we picture the gas as being molecules which just, collide. Tai Chi. Remember? Collisions. Okay. Number three, there's no force between them. So, you know, in chemistry, this could be positive and this could be negative, and what would happen? They get attracted, yeah? So, for ideal gas, we say there's no force, no attraction. And 4, we ignore gravity, okay? So we imagine the ideal gas is like small balls bouncing in a box with no gravity. Like here's a picture of it. This is what we picture. We picture the gas as being particles just moving around like this. Now in the exam, they sometimes ask you, what are the assumptions of an ideal gas? So I've given you 4 assumptions. First, the gas needs to be low density. So there's a lot of space between the particles. Number 2, that they collide. So they go like this. Number 3, there's no force between them. And number 4, we ignore gravity, meaning we don't care about gravity. It has no effect. Okay?
So there's no weight.
No weight force. So it's like, we picture it like it's doing this. Because if there was gravity, then maybe it's just like, it goes like this, you know, and all the gas just sits on the bottom. But we don't imagine that there's any gravity force. Yeah.
Okay.
So what you need to know for the exam is these 4 assumptions. And what will happen is they might ask you for like 3 of them. So you could say low density, colliding particles, no force, and no gravity. But this is kind of the same as number 3 anyways. No force. Okay, so can you carefully write those down for the ideal gas? No hat today, Ben. No hat.
Oh, in fact.
Okay. Bag. Yeah. Not bed. Yeah. Was Khalifa in this morning?
Yeah.
Maybe he doesn't like going to my physics class. Maybe. Maybe. Don't know.
I think physics class is the most interesting between like people come here and others.
It's a small class.
Yeah, so
What's your biggest class? Chemistry?
chemistry and maths,
Maths.
they're together
Maths. They're together.
with houses.
Oh, those guys.
Mm.
Those guys aren't interesting. They're boring. You got this?
Yeah.
Now, what are you checking, Summer?
WeChat, like WeChat. There's a chat.
Like Ren, QQ.
Oh yeah, it's cool, yeah.
I know many things.
I don't use that anymore.
Ah, that's old.
Yeah,
Nobody uses that. Not even I. I don't even use that. It's so old.
Yeah, so you use WeChat?
Uh,
Of course.
You have WeChat.
At a
I
friend.
have it on my phone.
Oh, sorry.
WeChat now on your phone.
Of course not. All right. So, what I want to do next is difficult. It's a proof, okay? In the exam, they don't ask you for this proof because it's too long.
Yeah.
What they do ask you is for a part of the proof. So, unfortunately, you need to know the whole proof because they could ask you for a part of it. Do you know what I mean?
A part of.
Yeah. They could ask you to prove just a part of it.
Yeah.
Because the proof has many steps. Yeah? I know, come on, English. What are you saying?
Start.
I was just saying what you say.
Yeah.
Yeah.
So, I won't go too quickly because it's very, very, very important you understand the proof, because they'll ask you a question to test that you understand the proof. Okay, so let's have a look at the proof now. Right, so what we'll do, this is how we imagine our gas. We picture it as like, to keep it easy, we picture it like it's in a box. Okay, so this side is L, L, and L. And we have our particle, and it's moving around the box, bouncing around like this. Okay? To start with, what we'll do is we'll just look at one wall and one particle, and we look at the particle just moving and it hits the wall like this. We'll keep it simple to begin with. So, we'll say that the particle has a mass m and it moves to the right with u. Then when it hits the wall and comes back, we'll say it moves with minus u. Okay so far? Yeah? Alright, so let's calculate this. Delta P. And we'll just make a bit more space. I'll write at the top here. Delta P. Who remembers what that's called?
Log L.
L? No.
Delta P.
I, yeah, what's that called?
I am.
I am, yeah.
I am P.
Yeah, so say it. You got the letter. IMP, yeah.
Impulse. In MPL.
Impulse.
Impulse.
It's called impulse, okay? And do you remember, and you said it's called I as well. Yeah. And that's equal to mv minus mu.
Yeah.
So here, that's equal to m minus u minus mu. So that's equal to minus 2 mu. Is that okay? Yeah? Okay. Now, next, what will I do next? What's wrong?
I forgot what is
What's what?
delta P.
Impulse. Change in momentum. mv minus mu. You forgot this?
I know the formula, but I forgot what
F.
Yeah.
它那个 E
Over delta t. Very good, yeah. What's wrong?
I just wonder what's Chinese
For delta p?
Yeah.
Do you know?
I know force is equal delta P
Yeah.
minus
Over
over
delta t.
delta T.
Yeah.
I know the force, but I forgot what is that.
Well, it doesn't matter. You only need to know it in English. Chun-Li, she's in Street Fighter, isn't it?
He says like some force, but it's not force.
It's like it. It's not quite
But
force.
It's like force.
It's
Okay.
not quite force. Guys, don't worry about what it's called in Chinese, because you have to do the test in English anyway, so
okay.
it's not important what it is in Chinese. So it's impulse. Okay. So what I'll do next, I'll divide by delta t. That's what you said.
Force.
Now, yeah, what is this? This is force over delta t. Now, remember the formula for pressure. Pressure equals force over area. So you could say force is pressure multiply area. So that's PA, is that okay? Equals minus 2 mu over delta T. Okay? Now before I continue, I'll just wait a minute for you to write this much down, and then we continue. Because there's much more. You got all of this, Ben?
Oh,
Continue?
Peter.
Yeah? Okay, so the reason for the minus here is because the particle moves to the left. So it's like the wall pushes to the left with some force. So the particle comes along and the wall pushes it backwards. So Newton said there should be a force this way, and that's called the reaction force. And that's the force that we care about, because when we look at a gas, we care about the force outwards, the force on the wall, not the other way around. So like here, I care about the force of my coffee against the cup. I don't care about the cup against the coffee. The only difference is the sign. So I'm not going to care about the minus, I'm going to care about the plus. I don't really care about the minus. I care about this force pushing out. Okay, so I'll just get rid of the minus. Now, what's the A? The A is L squared in my picture. Okay, right. 2 U. Now the delta T, distance, speed, time. So time is distance over speed. Now this, in my picture, it's going like this. Okay? So my question is, if you look at one cycle, you know, like it hits the wall, goes across, and then hits the wall again, what's the distance it travels for one cycle?
3.
Mm-hmm. All right. Like I'm picturing it's like here, and it's going.
From the middle.
Doesn't matter from where actually.
Two.
2L.
Oh, yeah.
2L. Is that okay? So there's a 2L here. So I can cancel that and that. So I get PL squared equals mu squared over L. So then I can get PL cubed equals mu squared. Yeah? But what's L cubed?
It's the whole.
Yeah, what's the word? What's the word?
Volume.
Volume. So this is PV equals mu squared. Yeah?
Yeah.
Now what does mu squared look like? It's like what formula? It looks similar to something we did in physics. Not MA, no? Yeah. Maybe to make it a little bit clearer, instead of using U, if you use the letter V, this is mv squared. That's like kinetic energy, isn't it? Except what's missing? What's missing? A half. So what we can do is we can put a half here and a half here. So now what do we have here? Kinetic energy. Okay. There's one problem though. Our problem is, in my picture it's moving like this, but in real life it's moving around like this in many directions. So we need to fix that now. Okay. So imagine this is moving like this. We can resolve. It can have a piece this way, a piece this way, and a piece this way. If this is U, then this piece here would be like Vx, this could be like Vy, and this one could be like Vz. So U squared equals Vx squared plus Vy squared plus Vz squared. Okay? Is that okay so far? Now my question is, you see this here? This u is actually like Vx, isn't it? Because in my picture it was just going like this. But these three here, these are all actually the same. Now does anybody know why they're all the same?
Because the L is same.
No. Imagine they weren't the same. Imagine that this was bigger than these two. What would happen? If the Vz is bigger than the Vx and the Vy, it means the gas is slowly moving up. But in the picture, we imagine the gas is going like this.
No gravity?
No gravity, yeah. So it must be that the Vx, the Vy, and the Vz, they're all about the same. Because if say the Vx was bigger, it means the gas is slowly moving left. If the Vz was bigger, maybe it means the gas is slowly moving up. So these three have to be the same. So what we could do is, we could say u squared equals 3v squared. So it means instead of having u squared here, I should have 3v squared. And this is a half p v. Sorry, I wrote that wrong.
Moves only.
Yeah, sorry. A half PV equals that's for, so I'm sorry, that's a bit confusing. That U, remember we said, is like Vx, and the Vx and the Vy and the Vz, they're all the same, so it's like V. So it means that what I need to do here to fix this is divide by 3.
What?
Isn't it?
Why?
Is it?
There's
No, sorry. Hang on, I'm confused. Wait, I need some
think you're
coffee
right.
first. I was right first time.
Yeah, you're right first.
No, first
No.
time.
No?
You said.
No, I was right the second time. It's 1 over 2 m u squared over 3.
Yeah.
Why?
Because the u here is like Vx.
Oh, the U is Vx. Why? Is the U is this?
Because remember when I got to here, it was
Because
using this picture,
yeah, the ball moves.
left and right.
Yeah.
So the u here is like the Vx in this picture.
Ah, okay.
So this here, you know what? I'll just replace it here. This is like Vx,
Okay.
and Vx is u squared over 3 in this picture.
Okay.
You see, I told you this proof is hard. This proof is hard. So again, I'll just stop here for a minute before we continue with the next part.
I'm a little bit confused in the from PA and converts to PL squared.
Oh, so A
Yeah, but
is this
It's the area.
area.
Yeah.
I don't know why. Cause when the first example, like moving like circle, PA, the area is not the point. Still see it's small ball. Why is whole wall is like the whole area?
No, for pressure it doesn't matter. So for example, if I have something small and it hits, say, this wall here, pressure, yeah, what's wrong?
Yeah.
Pressure is force over area, yeah? So you need to look at the whole wall.
It's not only the ball. It's when you push something.
Yeah.
That's the area of your hand. So
Yeah.
when the ball hits you,
Let me put it like this. If I push down here, if I say what is the pressure on the table, then it's the whole area. If I say what is the pressure on my hand,
Okay.
so I didn't ask for the pressure on the molecule. I said what's the pressure on the wall.
Oh yeah. Okay.
So it's a little different. Okay, it's difficult. All right, I'll wait a minute for you to get this much.
I already forgot the proof.
I told you this is hard. I told you it's difficult proof.
2 hours distance. Okay.
Yeah. You got this, Ben?
If the gas class
Mm-hmm.
as the water, but this U
Mm-hmm.
just cast a call.
Well, in my picture, I just drew it going to a corner. Sorry, we just picture it hits a wall. We don't worry about hitting the corner. It's too complicated. Continue. Yeah? So what I'll do, I'll bring the 3 up to the left. So that's 3 over 2 PV equals a half mu squared. But you said that's kinetic energy. Yeah? Now remember we said no gravity? So no gravity means potential energy equals 0. There's no gravity here. So you can say 3 over 2 PV equals KE plus PE, because the PE is 0. In other words, the total energy, the kinetic energy is the same as the total energy, because there's no potential energy. Like that. Yeah. Now look, you might say, okay, well what about now if instead of having 1 particle, you have 2 particles? Does that change? Or if you have 3 particles? Well, the only difference if you have n particles is that there's an n here. Right? Which means there's an n here and an n here. But it's still total energy. You just add them all together.
So is it times n?
No, there's instead of writing E, I'll just write total E. Total energy.
Yeah, I mean if we have
So
n,
if you have n.
n molecules.
If n molecules, yeah.
So.
It just means this is the total energy. Total energy. Yeah. So you can finish by saying total energy is, oh sorry, I have it there. Total energy is 3 over 2 PV is the result.
Oh, what's P?
P is pressure.
Oh, that's too long.
It's difficult. It's difficult. So what does this result tell us? It tells us if you know the pressure and if you know the volume, then you know the energy in the gas. That's what it says. And that's actually very useful. So if there's more pressure, what happens to the energy? More energy. If you have more gas, then you also have more energy. So it's a very important result in physics.
Last word. Last word. Last word sheet.
它 v 越大，然后那个
Come on, English.
the value is big. If the value is bigger than before, the Ku will bigger.
Yeah, if the pressure increases, the total energy increases.
Bigger,
Yeah.
Because it's it's dependent on the P and the value.
So
Yeah.
is value change?
The value change, the total energy is increased.
Yeah, well, think about it like this.
So when you give a box a pressure, maybe the box will be smaller.
No, I understand. There's another formula. It gets a little bit complicated. This formula, I know what you're saying, like if you change the shape. That's not really what I'm saying here. I'm saying if you have a gas, this is how much energy is in it. Now, if you start to change the gas, it's a different formula. Like, for example, take this room. This room has air in it. I want to know what is the energy of the air. So, I know the pressure and I know the volume, so I can calculate the energy.
Okay.
But we can use it in every questions. That use 3 or 2 PV.
I'll explain how to use it now.
Yeah.
Why is this important? Because this here is big and this here is small. Which is easier to calculate? Is it easier to calculate this or to calculate this?
Sigma.
Yeah. Could we measure the speed of every molecule and get the total energy this way? Is this possible? No, of course not. Think about all the molecules in this room.
We can't calculate.
We can't calculate. But can we calculate PV?
Yeah.
Yeah. So this gives us an easy way to get the total energy without having to calculate it one by one. Do you see why it's so important?
Yeah.
We can get the total without having to calculate it individually.
Yeah. All kinds of the gas we can. That
No, ideal gas.
ideal gas.
Yeah.
Just ideal gas.
Yeah? Can I continue?
Yeah.
I just want to show you when you can use this, okay? So look. Imagine this is infinite, 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 and you have a gas here. If it's infinite, this gas, it's not really important because it's just spread out in a very big space. But imagine then you put the gas in a small space. So the gas is in here. And the gas has a pressure and it has a volume. In this picture here, the molecules are not moving and they're spread out infinitely big. And then you get them together and you put them into a small container and they now have a pressure and they now have a volume. The energy to go from here to here is 3/2 PV. In this picture, it has no kinetic energy. So the energy here is 0. By putting the gas in a box with a pressure and a volume, it needs this much energy to do that. Okay? Do you get the idea here?
Yeah.
This is like the energy you need to trap the gas. Yeah, like to trap it. Yeah?
But it's same formula.
Yeah, that's what I'm saying. It's this formula.
Basically.
Now, I know, there's a different formula. No, I know what you guys are thinking. Listen, if I now change this box,
Yeah,
that's a
just-
different formula. That's a different formula.
Okay, so
This-
from the bigger to
Yeah,
the
yeah,
smaller.
this formula here is to trap the gas.
Okay.
And then when you start to change it, that's a different formula. Is it okay?
Yeah.
Continue?
It's
Yeah.
zero, like
Here,
it's zero.
It's
because
zero.
There's no pressure.
because it's not moving, there's no pressure.
There's no
The-
moving. The molecule
Yeah,
is not moving.
In this picture, we imagine they're not moving.
Imagine.
Just imagine. Because, you know, we're just imagining it's infinitely big and they're not really moving.
I'm not really.
Not
moving,
really
it's
moving,
small.
yeah, yeah, yeah. And then what you do is you collect it together and you put it into a container. So now they have a volume and they have a pressure. So you need some energy to do this.
Can I imagine that I use the key to let the gas into this air?
Yeah, it's like this. Look, yeah. It's like this. So imagine here, look, this is very large. Okay? And the pressure is nearly zero. So it's not really moving. Okay, so we can imagine like it's very large, infinite, and the pressure is zero. This isn't really moving. And then I put it into a small container, and now it's moving fast. The energy I need is 3/2 PV to do this. Yeah? Now, let me give you an example of the exam question. Okay? So I'll ask you, see if you know. One year they asked the students, in the formula for kinetic theory of gas, of ideal gas, why is the 3 in the formula?
Why is what?
The 3 in the formula.
Because
Yeah.
the speed of the
I know you can keep it simpler. Simpler than this.
Because it's not ideal.
No?
So it's not moving like circle.
Yeah, so like that, let's give a sentence here. Why did the 3 appear?
It's
Because,
moving in the weather.
yes, that's it, very good. Because it was moving in a volume, in 3 dimensions.
3D. Yeah.
3D, yeah. That's why the 3 appeared. Because we were just doing it in 1 dimension. So then it makes you think, if the gas was in 2 dimension, like this, then this wouldn't be a 3. What number would this be instead? It'd be a 2. Yeah, so just PV. So the reason for the 3 is because it's moving in 3 dimensions. Another year they ask you, what is the cause of the pressure? So what is the cause of the pressure? Yeah. What is the reason for the pressure?
It's the same. Because it's in.
Not quite this, no. If you look at the proof.
Direction?
Yeah. So what was the cause? Yeah.
Because the gas
Yeah.
the gas
Yeah.
molecules
Yeah.
need move, and
Yeah.
if you don't have this things, they will go to.
Yeah. So I need one word.
Limiting.
No, not this. The cause for the pressure is because there was a collision between the molecule and the wall. Collision, crash.
A crash.
Yeah, collision. Because look, go back to the proof. Okay? why did we have a P? We had a P because we had an F.
Yeah.
Why did we have an F? Because we had a delta P over delta T. Why did we have that? Because we had this. This is the collision with the wall. So the cause for the P here is the collision. This is the cause. This is the reason. You understand?
Yeah.
You see, it's difficult. It's difficult. I know it's difficult. Yeah.
So why in 2D is PV?
You told me it was PV.
Yeah, but when I saw the proof,
Yeah, well, look at the proof.
because in 2D, in the first.
Yeah, no, look. The tree here
Uh-huh.
is because of the tree here.
Yeah.
And the tree here is because of the tree here.
Yeah.
And the tree here is because you have 3 of these. And the reason for the 3 of them is because it's 3D.
Yeah.
If it was 2D, it would just be u squared equals vx squared plus vy squared.
Yeah. So, but what's the first conditional? What's this? It's not 2D.
Oh, and we looked at 1D to begin with.
Oh, that's 1D.
Oh yeah, all of this is 1D. And then here we change to 3D from this part.
这是什么？1D 是啥？直线吗？
不是它，我 can I use Chinese?
Go on.
English, okay, English.
Okay.
You can use Chinglish. You can use some Chinese and
Yeah,
English.
yeah.
Okay.
Yeah, if the molecules move, just hit the things, and the molecules go straight, just hit. Yeah.
That's 1D.
Yeah, it's 1D, and if the molecules must move inside of the box, these
It's
things.
3D.
Yeah.
3D, yeah.
So hey, maybe move to here.
Yeah.
Yeah.
I never heard 1D. 1D is
1D is just this.
1D is a
Yeah,
straight, and
straight
the
line.
2D is yeah.
Like this.
Yeah.
This is 1D.
Yeah.
This is 2D.
Yeah.
that's
And this is 3D.
3D. Yeah.
oh, so it's linear.
Linear, yeah. So,
Never heard 1D.
so it makes you realize that if you had 4D,
It's 2PV.
it would be 2PV, wouldn't it? Yeah.
Four.
4D, yeah.
4D.
Good question, yeah. Just
So
something to
how
think
can-
about.
How can you move like
I can't draw 4D. I can't draw 4D.
No one.
But my point is, if you have ND, the bigger the N, the bigger this number, which means more energy. And if this is smaller, then this is smaller, there's less energy. Yeah? Okay. Did you write all this proof down? I think it might be good to write down a couple of example exam questions. So one example exam question they could ask you is, what is the cause of the P pressure? Another question is, what is the reason for the tree? And another question is, what are the assumptions for the ideal gas? Assumptions are what we said at the start: low density, colliding particles, no gravity.
The last one.
How to spell it? AS?
ASUMP. Yeah?
Yeah.
What's how to spell the word? Is it like crash?
Collision.
How to spell
It was the name of one of your lessons.
Really?
Yeah.
No, did you do this lessons?
Which?
Give me that.
Collision.
You're going to...
我这个词儿啊， Cantilever.
Paige, look, look, look.
Oh, okay. He's in brackets.
Ah, come on.
Okay,
You
okay.
guys are driving me crazy with your English. Continue.
What is
For which one?
sorry?
The answer is what I told. Give me your.
For
Yeah. Continue.
what's P?
Pressure.
Ah,
Yeah, what is the cause of the pressure? The collisions, yes.
The collision is delta is I.
The delta P from the collision, yeah. Did he just ask you what does collision mean? Did he ask you what collision means?
I just,
Because
Clear.
I'll slap you if that's what you ask.
I just write 3D.
3D, yeah. Oh, just 3D? Ah, no, give a sentence. A sentence at least.
Because of 3D.
Moving in the street.
Thank you. That's, you should have a verb because it's moving in 3D. What?
What?
I want to slap Summer.
Do please.
All right, let's continue now. So, this is our formula.
Jeez.
Okay, right, this is our formula. Right. So, it may seem like we know how much work is done when a gas is changed, the pressure and volume. However, it doesn't tell us this. We were talking about this a lot. So what we're going to look at next, Gao, is, and I think who was asking me, Gao or Summer, one of you were asking me, what is the energy you need to change the shape of the gas? Maybe you want to make the gas smaller or make it bigger or something like this. So, yeah, you think you know?
You know.
You know.
You know.
I know. Do you know?
2D.
Yeah.
Maybe just one.
Yeah.
L square.
Yeah.
But I think 3D is more.
What?
You will
LQ. Yeah.
crush 6 L. 6?
No, I know what you're saying because the 6 sides. But when you look at the area, remember it's only for the surface it collides. You don't care about the other areas. So it's still just L squared, not 6L squared. Yeah. Good question though, because you're picturing the full area. Can I continue? Yes? So look, next part. So imagine we have something like this, and there's a pressure, like a can, yeah, it's a pressure and a volume. Okay? And then what we do is we have some force here, and the force causes the shape to get smaller. Okay? And we would like to know how much work is done here to reduce it. Okay? So, what's the formula for work? Work equals force times distance. So, we'll call this here D. Okay? Yeah? What?
It's same.
X.
It's same.
We talked about this, it's the same.
Yeah,
Oh,
it's
okay.
same.
We talked about this many times.
I can't remember. I only can remember one thing. You know, size is.
Try to remember 2 things, okay? Right, so force, we have the formula pressure is force over area. So this here is P A D, okay? Now, if you look here, I know this might be one topic for today because there's a lot to do in this lesson, as you can see. So, if you look here, this is the A. Focus. This is the A, and this is the D. So, what is A times D here? If you have
What is A?
A is the area here.
Volume?
Is
Volume, but volume of what?
of the,
of the can?
Yeah.
No, because this is the volume of the can.
Of the compression.
Yeah, it's the reduced formula. The reduced volume. It's this volume here.
yeah.
Yeah.
So we can call that delta V, like the lost volume, the reduced volume. So if you want to calculate the work done, you need to calculate P times delta V. So if you make the volume smaller, this requires some work to do this.
So
Yeah.
from the whole change the smaller. It's just a minus.
No, not minus. So this is the work. So okay, just to be clear, this is the work required to reduce reduce the volume by delta V. So if you want to make it delta V smaller, you'll need to do some work to do this. How much work? P delta V. So the more you want to reduce, the more work you need to do. Yeah? Is this proof okay? It's easier than the last proof.
Yeah.
Yeah? So if you can write this screen down. It's okay? Now look, you can think about it like this is what you get in and this is what you get out. So you do some work and you get less volume. But there's another way to think about it. You could think about this as in and this is out. So you know in a car engine, you have a gas here and then the gas explodes. And this causes this to move down. And this turns the wheel. You know, in a car engine. Yeah? So the petrol goes in, there's a small explosion, and the volume gets bigger. So this makes some work come out. So you can go both ways. You can put work in and get less volume, or you could get more volume and you get work out. You can work both ways. Does anybody know what this is called inside the car? It's called a piston inside the car, you know, and it gets big, small, and it makes the wheel turn around. It's called a piston. Yeah?
Is the V bar, V8, V6.
Yeah, like this. Yeah. So, like most cars, I think, have 6 pistons.
Most cars. Sport car have 8.
Yeah, sports car has 8.
Yeah.
A small car has 4.
4. Yeah.
Like Nissan Micra or Toyota Yaris would be 4. But like a normal car would be 6. Yeah.
No. Normal car is 4.
Is it?
Yeah, because the if you want more power and more higher speed,
It's 6.
the number is higher.
Yeah. And the reason, because if you have 4, you get 4W, but if you have 6, you get 6W, which is 50% more. Makes sense, yeah? Okay, continue. Yeah, okay, that's our formula. Right, now, another proof. More proofs. Next, we'll consider the pressure on a sphere submerged in a liquid. Yeah, actually, not a sphere. Sorry, I think I'll do. I think I meant a circle. A circle. Anyways, don't worry. I'll give you the formula here. So, imagine you have some gas or liquid, and then here you have some area, and it's a distance h here, and here you have some pressure. Yeah. What happens to the pressure if the h is bigger? Do you get more pressure or less pressure?
What's this?
Well, like if it's underwater.
Underwater.
Yeah. So if the h is bigger, do you get more pressure here or less pressure?
What more? Oh,
More pressure. You notice if you swim underwater,
yeah.
if you go down more,
Yeah.
then there's more pressure.
Yeah.
Yeah.
More pressure.
Let's calculate. Okay?
Sorry. Is only this one. It's no the value of base energy, relative energy.
Say again?
Like if you change the shape,
Yeah.
size,
Yeah.
so there's only work-based value. It's not energy-based value.
Yeah, it's the work done to change the volume.
So we don't calculate some gas inside.
No, you don't. You don't. No. Okay, so let's calculate the pressure. So what's the formula for pressure? Force over area. What is the force on this? The force is because there's water on top of it. The water is pushing on it.
Yeah.
So the force is actually the weight of the water. Okay, what's the formula for weight? mg.
Okay.
Now, if I use this formula, density is mass over volume, then I can change this into the m is rho v. So this is rho vg. And what's the area here? Area is pi r squared. Yeah? Now, what's the volume? The volume is pi r squared h, the volume. Because the shape is like this, cylinder. But look what happens. This cancels with this. So you get pressure is rho g h. And you don't care about the size. So you could make the or 0. So the formula is true even if it's just a point. And you want to know the pressure on the point. That's the last formula, don't worry. So if you write this down.
I remember this.
You remember this one? Yeah, this is the proof. Have you seen the proof? Okay.
But not really
Don't.
about proof.
Okay. In this lesson we do.
I think if we have the physics class in the morning,
Yeah?
it's better than afternoon.
Are you sure?
Yeah, I'm sure. Because in the afternoon, everyone is tired.
Me too.
Yeah.
Me too.
If in the morning,
Yeah, but you're young. You should have lots of energy.
I'm not young, they are young.
Younger than me. Okay. Who's the youngest? Ben?
Then
And the oldest?
me.
Well, no, actually, how old Khalifa is? How old is Khalifa?
He's youngest.
He's the youngest.
Oh, yeah. Khalifa is the youngest.
70?
He's minor, isn't he? Yeah.
You're adult.
Yeah, I suppose you're adults.
So, is that impossible if, cause I have a friend who thinks the PMP class is not that useful than us.
Depends what they want to do.
Yeah, but
Yeah.
like a few people say they always learn the same things, and they compare with me because I calculate every day like this.
They're very different. Really, in PMP, it's mostly English.
Yeah.
You're doing English all the time, every day. It's not like IFY. You're not doing things like this.
So is that possible to change from PMP?
Well, the PMP is only suitable if you are finished university.
Yeah, I mean, it's not I change, it's the person who want to change to this class. Like, the calculates, they want to do something.
I understand this.
They want more work. That's
Yeah,
what they want.
yeah.
Is that possible to change?
Well, I don't have any problem if the PMP students, if some of them want to join this class to learn something, that's
No,
fine.
they won't change the course totally.
It might be a bit late to change, you know, like it's already, what's this, like week 6 or something?
Yeah, but
But for
The person-
Chinese,
they just want, they don't want to waste time, they think. That's what they
They
want.
can talk to their tutor. It's possible to change, but maybe it's no good for them because if they want to study a master's, they need to have a PMP. You know what I mean? Like the IFY is only good if you want to study university, you know, from the beginning.
I agree.
Yeah. But you need PMP if you want to do a master's. Yeah. Okay. Next now. Oops. So look, here's you. There you are. And here is the air. And you know actually, for the same reason, the air is pushing down on you. So this causes a pressure. And this pressure, we call this 1 atmosphere. And 1 atmosphere is equal to 101 kilopascals. So actually right now, there is 101,325 pascals.
It's really big.
Yeah, this is it. It's really, really big. And you don't feel it.
Why?
Because
because
you're used to it.
inside of the body, if you don't, the Pascal is bigger, and you will be.
The thing, what he's trying to say is, you don't feel this pressure because your body pushes back.
Yeah.
And your body is strong enough to push back and to cancel it. You only feel this pressure if it changes. So for example, if you go down very deep into the earth, like maybe 1 kilometer, you will feel more pressure. So your body will feel the extra pressure because it's not used to it. You know what I mean?
But
Or,
always go higher.
yeah, if you go up, there is less pressure and your body will feel this because it's not normal.
It's not comfy, I think, more higher.
Yeah. This is the normal level. Your body doesn't feel it because it doesn't notice it. Do you know what I mean? Like, because it's constant.
Which one is more?
More pressure is when you go down.
No, but when we go down, it's not like if you're hiking,
No, if you're hiking, there's less pressure.
but you feel more bad.
Yeah. It's not good for your body. Because your body is built for this pressure. If you have less than this pressure, your body, it's not built for this. You know what I mean? Like it gets confused.
So the people live in the higher, how to say that?
Yeah, the mountains, yeah.
The mountains.
They used to this.
Yeah.
They're used to it, that's the thing. You can get used to it. So maybe if you were born in the mountains, your body is used to it.
So when they get in the city, they won't be used to.
Exactly. So if you live in the mountains and you come down to ground level, the first thing you'll notice is your heart, I think, beats faster. You get very, very hungry. You're not used to this pressure.
It's like way going down.
It's like if we were here and we went down here, yeah. Yeah, see, you just get used to it. So this is called 1 atmosphere of pressure.
Okay.
Okay, so if you can write this value down.
So when we go down, we will feel hungry. or
Yeah, I think maybe so, yeah.
But when I usually hiking.
Yeah.
So when we're hiking, we will feel dizzy.
Dizzy, yeah, correct.
Hard
Yeah.
to breathe. something
Hard to
like
breathe, correct, yeah. Yeah, yeah.
that. So if we go down, we feel hungry. Just hungry. Nothing.
No, I think there's other things too, like maybe,
It's different feeling. And then
Yeah.
we go down like 1 kilometer.
yeah, it's not normal, you know.
But before when I was in China, my gym was in underground. That's a little bit hard to breathe because after the exercise,
Yeah.
you feel
Yeah,
not
yeah.
good. It's like too hot or something.
Yeah, yeah, yeah. Okay, you wrote this value down? This is called 1 atmosphere of pressure. This is the normal level of pressure, like right in this room right now. Yeah? This is a really big number. It's really big. Yeah? Okay. So, let's have a look. Let's see.
So
Yeah.
when we just walk in the space
Yeah,
and we will boom.
yes.
We feel
Oh.
warm.
It's
No,
boom,
not really.
or
No, you'll expand. Because look, this is you.
We feel
Yeah.
smell.
Hang on, I'm drawing you.
I
Okay.
like ginger man.
Yeah, gingerbread man, yeah. So this is you. So your body
yeah.
thinks there should be 101,325 Pascals. So your body is built to push
Yeah,
back. If this is gone,
yeah,
then it continues to push.
yeah. Boom.
Well, no, not really. Explosion. No. You swell. You get a little bigger.
No,
So-
in the space.
I don't think you'll explode. This is just from movies.
Yeah.
It doesn't really happen. What will happen is you'll just swell. You get bigger.
Then you are.
You will, and then you'll die.
Yeah.
Yes. Yeah.
Oh, that's why when people die, they were getting bigger. The body, the corpse.
It depends on how they die. There's many reasons. You know, if you die in space, you'll get bigger.
But usually when the people die, like after 20 days, or they were getting bigger, there's something.
The reason for that is when your body breaks down, it releases gas, and this gas builds up inside you.
It is getting really bigger, like.
Yeah.
season.
Because the gas inside you expands then. Okay. What is the pressure on you if you're swimming 5 meters under the sea? So, what formula do we need to use there? Pressure equals rho GH. Okay. What's the rho for water?
1,000.
1,000.
Sorry.
The G, 9.81 and 5.
Yeah.
Yeah, C, underwater.
Yeah.
Oh!
Salt water?
Hang on, thank you, Ben. 1030. Very good. 5. And that's the pressure. Okay, so that's fine. How thick is the Earth's atmosphere?
Who knows?
We can calculate.
Really?
Yeah, so here's you.
Thick.
Yeah, correct, yeah. Here's you. Here's the atmosphere. Or just to be clear, here's the air. Like, what's it? Oxygen and nitrogen, isn't it?
And CO2.
CO2 as well. Okay? And we want to know how thick this is. Now, before we calculate it, roughly how thick it is. So tell me this. How high do you think you can go before you can't breathe anymore? What do you think it is? Roughly. Think about a tall mountain. Like, what's the tallest mountain? In English?
8,000.
I think the tallest, maybe it's like about 8,000, something like that.
The
So,
Chinese one, that's what he said.
yeah.
I can't remember the name.
would you agree that maybe it's about 10 kilometers? Maybe something like this. Okay, let's calculate it. So, come on. When I put it down, come on. So look, here's the ground. So you can think about it as like you're under air. You know, like underwater, under air. So if I use this formula, pressure equals rho GH. We know what the pressure is. What's the pressure? 101,325. Does anyone remember the density of air? It's really small, it's about 1.3. 1.2, 1.3? 1.2. The G? So you can calculate the H. You can calculate the H. Let's see. Well, let's just over 1.2 times 9.81. So what's the H?
8,607.
What is it?
8,607.
Yeah. So it's 8.6 kilometers. Yeah? Roughly. Now that's only a rough estimate because if you look at this formula, there's a small problem. If you go up to the top here, the G is actually smaller up the top. And also the density changes. So here you have the density is bigger and here the density is smaller. You know. So for me, I think this would be maybe too small. You could say I would estimate it as being twice this big. Roughly twice this big. So I think it'd be about maybe 16 kilometers. So I don't know what the true answer is. I think the true answer is like maybe 10 or 12. But you can get a rough answer. You know, we think the answer is about something like about 10 kilometers. Because you said in China there's a mountain which is 8 kilometers. And I think the biggest mountain in the world is 10 kilometers. So it's something like this.
So
We can estimate.
how can I get T?
Oh, this is it. It's about this.
Is T?
Yeah.
It is not high.
Well, I just care about
This.
what we can breathe. You know, I'm looking at the pressure from the low level, the oxygen.
How thick is the top?
Oh, I know it's very thick because then you have a next layer here which is like O3, isn't it? Yeah, ozone. Yeah. No, I don't care about that. I'm just looking for this one here, because in O3 the density is nearly zero. It's very low. Yeah. Okay. Right. How are we doing? Good. Good. So we'll just have one topic today because it's quite a big topic. For the last few minutes, I'll let you try. How many questions have you got? Did you get your questions finished yesterday?
Unless 4.
Except you got 4 done.
Oh, one please.
Oh yeah. Okay. Yeah.
It means is this is you can see the answer.
Yeah.
All of this
I
is
think-
English.
Yeah. Yeah, that's good.
I don't think I can write something.
You can practice. Okay, if you do these ones now, the next page.
So that you only copy
Straight up.
sing.
Did you do this yesterday?
Don't.
Oh, Gow, you were supposed to do this for homework. This was homework.
I do that today.
Okay,
I
this is
just-
for now.
Okay.
So
By the way, Summer, that was an exam question.
exam question.
This one was number 1, yeah.
Easy.
Oh, I have a question for
Yeah.
calculator on.
Yeah?
How can I use log?
do you
But
mean?
this log is only 10, log 10.
Oh yeah, this is log E.
Yeah.
This is log E.
LN.
ln.
Yeah, how Could we put in like a log 2 or
You
log
can't.
Oh, we can't.
Not on this calculator.
Oh,
No.
no.
Only this
On this-
one can use.
Maybe on this one. Yeah, on this one he can. Not on this one.
放弃吧。
It's 27 euro. 27 euro. Could you imagine? 27 divided.
€27 and you can't even change the log.
Let me try.